as this thing dings. There we go. All right, so today we're gonna just start off with doing a couple derivatives, right? And you have a couple options here, right? For number one, you can just multiply it all out and then take the derivative using the addition and subtraction rule. I think that'd be easier, right? You could also write it, well, if you are gonna multiply it out, you're gonna have to split it up anyway, so you have to write it like this as two binomials, right? So 2x plus 3 multiplying with 2x plus 3. And that's what that represents, by the way. That's what that represents. When you have something squared, you're just writing it twice. And in fact, that's the same thing that's going on for the second one right here, except you're not writing it twice, you can be writing it 3 times. Now, you could use the product rule here. The product rule does work, where you take the derivative of the first function, multiply by the second function, then take the derivative of the second function, multiply by the first function, and then simplify or not simplify, right? That works. You end up getting, let's do it that way real quick. You don't have to do it this way, but let's do it that way real quick. Derivative of the first is going to be 2 times the second function plus the derivative of the second times the first. Wow, it looks exactly the same, doesn't it? Which kind of makes sense because, well, they match. All right, so I have over here, this derivative right here is going to be equal to, if I simplified this out, this is going to be 4x plus 6, right? Is that right? 4x plus 6 plus 4x plus 6. Why, that just gives me 8x plus 12, doesn't it? And if you multiplied and FOIL this out instead, you'll see that f of x, right, is the same thing as FOILing this out. That's going to be 4x squared. 3 times 2x is 6x. 3 times 2 is 6x. That's going to give me a plus 12x and plus 9 at the end. And if you take the power rule here, I hope you see that you get the same answer, right? The power rule for 4x squared comes out to 8x, and the derivative of this uses the coefficient rule, and you just get 12. And that's the same answer that you would get this way. Which way do you want to do is up to you, right? Which way you want to do is up to you. Some ways are quicker than others. I'd say probably multiplying it out would be quicker. But I leave that to you. Now, when you come to number 2, on the other hand, product rule here is going to stink, right? Because there's 3 of them this time. And I never taught you the product rule for more than 2 functions. 2x plus 3, 2x plus 3, 2x plus 3. There is a product rule for more than 2 functions, by the way, but it's just not a common thing that's taught, right? It's just not a common thing that's taught, but there is one. It's not that bad either. It's just extra rules when there's easier rules that could be applied for this. And that's what we're going to learn today, because this just gets kind of tedious. Even FOILing it out is a little bit tedious, right? Because then you're going to end up with 4x squared plus 12x plus 9, because that's what I showed that multiplies to. And then you got to distribute another 2x plus 3 to that. And then you're going to get this long, wait, I shouldn't write that. That's not the derivative. That's just the function, right? And then that's just this long polynomial that you have to distribute. Or you can go ahead and try to apply the product rule right here, labeling this as your f of x and as your g of x. But again, I wouldn't bother doing that. That just gets you. That would be your like last resort. You have the tools to do it. You can do it, and you will get the right answer. But we have an easier way. Okay, we have an easier way, and that's what today's lesson is going to be on, right? Today's lesson is going to be the idea of differentiating using the chain rule, right? So if you're writing that down, we're looking for this guy right here, the chain rule. Okay, and the chain rule is for functions that look like this one up here, both of them actually, right? Both of them. These are ones that would use the chain rule to make your life a little bit easier when you're taking the derivative. Okay. So let me show you functions that will use the chain rule, and let me show you functions that will not use the chain rule. Maybe you can kind of see the idea, right, of what is going on here. So this one would use, right, the chain rule. And on the other side, we'll say that these ones don't need the chain rule. So for example, one function that doesn't need the chain rule, right, I hope you guys can see, is just y is equal to something like x squared plus 1. Right? We don't need the chain rule for that. We just use the power rule, you get your derivative, and that's fine. What's something that might use the chain rule, or can use the chain rule, I should say, that can use the chain rule? Or actually, I guess I should say, not can. I think a better word would be must. Let's go with must use the chain rule, right? And don't need chain rule. That just sounds weird. It's fine. Anyways, something that must use the chain rule would look something like this. Let's say I have that same function, x squared plus 1, but I have it inside another function. So I have here the square root of x squared plus 1. Right? Let's keep going. Let me list them all these. Let me list a few of these out. Another function where you don't need the chain rule. Let's say I have, for example, y is equal to sine of x, right? Derivative of sine of x, we already learned that from the last chapter, is cosine of x. One that would need the chain rule is if I had y is equal to sine of 6x. Okay? Another one up is like our warm-up, right? What if I had something that was asking me to take the derivative of 3x plus 2, and then I was comparing that to take the derivative of 3x plus 2 to the fifth, right? Are you seeing a little pattern of where we are forced to use the chain rule and where we don't really need to use the chain rule? Hope you guys can see it. If not, you will see it by the end of today, right? The idea is, if you remember, if you were taught about functions, you might have been introduced to these things called composite functions, right? And everything on the right over here is a composite function. It's a function that can be placed inside of another function, right? That's what a composite function is. Now they have crazy notations if you look online and you look for definitions of these things. They go things along the lines of like saying, if y is equal to f of u, don't giggle, right? And they say that it's differentiable, right? They have a differentiable function called u, and u is differentiable, right? And u is equal to g of x, right? And you've seen this before. That just means basically that the y function can be written as f of g of x, meaning you have a function inside another function, right? That's all it is. There's one function placed inside of another function. So for example, the one we were looking at right here, when you have y is equal to the square root of x squared plus 1, right? I would say the outside function, right? The outside function, f of x, is equal to the square root of some stuff. Whereas the inside function, g of x, for example, is x squared plus 1. So what I'm saying is when you write something like this, f of g of x, right? The f function is the square root of some stuff, right? Let's call it square root of x. Okay? And all I'm doing is when I'm plugging in a function inside another function, I take what I have here and I just plug it in for wherever x is. So if I ever see an x, I plug in the stuff in for it, and now I have a function inside another function. Okay? Are you guys okay with that? The idea of what a composite function is? It should be a review, but if not, let me know. And it's one of the common mistakes that students make when we get to this chapter is seeing a function inside a function, right? Best way I can tell you is like, I don't know if you guys ever had a blow pop before or a Tootsie Pop. Have you guys ever had one of those candies? We just had Halloween. Did you guys, anyone get those? They still have blow pops? I don't know if that's a popular thing. You guys, let me know. But if you've never seen a blow pop, let me show you that real quick. Right, it's the sucker that has gum in the center of it. I don't know if you guys have ever seen it. These are Tootsie Pops. Oh, that. Yeah. Let's see here, blow pops. They're these guys, right? And if you look in the middle of a blow pop, there's always gum. I don't know if they're still hard, but back in my day, they were terrible. Like the gum in the center was like horribly, horribly hard. And, you know, everyone loved it though, right? But if you cut it in half, you'll see something inside, and you have a candy outside. So there's a gum center, and then there's a candy outer coating. And when I look at composite functions, that's what I think of. I think of a gum center, right? So g of x is your gum center, and then your square root of x is your candy coating. It's the thing that coats around the gum. Does that make sense? Right? You have a function surrounding another function. That's all a composite function is. It's something built on top of another function, right? Or better yet, a function that's crammed inside the other function. That's how I like to think of it. Now, I want you guys to see if you can decompose and see which one is the inside function, right? And which one is the outside function? Which one is the bubble gum and which one is the candy shell? And I want you guys to write this into the Pear Deck. So let me go ahead and open that up real quick. Let's get a new one that's blank so I can save these answers from before. There we go. Let's go over to this slide and see if you can identify which one's inside and which one's outside. Okay, let's go with two examples here. So the first example, right, identify, right, inside function, and you get to call it, by the way. Do you want to call this, you want to just keep it consistent? Let's call the inside function g of x, right? Right? And the outside function, wow, I just do 3 triple quotes there. Outside function, let's call that f of x. So I want you to identify these two functions for me, right? For these example problems for me. So let's take a look, see if you can identify. Let's go with the first one. Why did I write number 2? Yeah. Let's go with the first one. All right, see if you can identify the first function. And what's on the inside, what's on the outside, okay? Let's go with something easy to start off with. Let's say I have here parentheses 3x plus 5 to the 4th. So tell me what's the inside function, tell me what the outside function is of that. And if you can get that one, try this one. Try this one, see if you can get this one. This one's a little bit more difficult, right? Let's go with this one. Let's say if you can tell me what's the inside function, what's the outside function for sine of 2x. You know what? Let's go one more. Let's go one more. And if you can do that one, this one will be a little bit more difficult, but see if you can figure out this one. What is the inside function and what is the outside function for tangent squared x? There you go. Tell me what the inside function is. Tell me what the outside function is for this one. We'll give you a minute to write that down. So just write down number 1, f of x, g of x. Number 2, f of x, or g of x, f of x, right? Because you want to do inside, then outside, or it doesn't actually matter, however you want to write it. But identify the inside and the outside function for these composite functions for me. You're basically decomposing these composite functions, right? Let's go ahead. 1 minute timer. I want to take a look at some of your answers here. Let's see how you're doing. There we go. Aside from that, guys, how are you guys doing today? You guys doing all right? Hopefully you're not too anxious about election day. I'm just not going to look at the news today and just wait until tomorrow. I've already went out and voted, by the way. Voted by mail because I don't want to deal with the crazies. Oscar, thank you for that first one. That looks beautiful, by the way. Something to the 4th power, though, the way we denote it, you might want to put parentheses there. So you put parentheses and then to the 4th, or you can put x to the 4th if you want. And x is your placeholder for that. That's the beauty of that. Okay, let's take a look over here. Let's keep going. All right, I'm going to stop that there. David, that's exactly what I was saying, right? X to the 4th. X is your placeholder for that stuff, right? Right? What the? Why did you draw dots over them? They were good, David. They were good. Yeah, beautiful, Gracie. Beautiful. Keep going. Keep going. Monica, not bad. Not bad. I like that you drew the foreign. That's awesome. Be careful with number 2, though. The function for number 2, for the inside function is, you're close. Not quite there, though, but you're close. Jocelyn, beautiful work on the first one. Keep going on that second one. The second one looks good. I like that one, Kimberly. That's awesome. That number 1 is beautiful. Leslie, same to you. That number 1 looks beautiful. Joe, awesome job. Beautiful work. Max, beautiful work. Emily, can you go back up on the notes real quick? Sure. All the way up for this part where it says you must use the chain rule, you don't. Chain rule. Oh yeah, that's this one. Yeah. Okay. Get that real quick, and then I'm gonna slide that back. Oh, get out of the way. There we go. Oh, by the way, this is a great way for me to plug this link. So, all right, you got it, Emily. Good. But this is a great way for me to plug this link. If at any point I'm doing these notes and I go too fast, right, and you want to catch up on it, you can always go to my Canvas page. I know this is, some of you already know this, but I just want to plug it. So if you go to my Canvas page, on the home page, not on the weekly agenda, if you go on the home page, right here where it says notes, and it says period 3, this is being updated live, right, on OneNote. So if you click on period 3, you can see all the notes that we've done in the past, including the notes I'm writing right now. And it's not one of those things like, oh, what if he hasn't put them up yet? This is connected to it, directly to it. It just takes a little bit to load. So if at any point I don't catch your message and you're like, oh God, I need him to go back, or you're too shy to type it out, right? You can always go over here. Look, Unit 3, I literally created this today. Oh, look, also it has Unit 1 and Unit 2 stuff on there. And check this out. You click on Unit 3, right? Everything I've written out today is showing up right here. So there's the chain rule stuff that you might have needed. So you can actually bring that up on your own screen, right? And you can scroll through and see, oh, this is where we left off right here, right? He's about to write some stuff. And that's what I'm going to do right now. Let's take a look. By the way, I was still going through some of your answers I wanted to see. Angela, awesome job for the inside. You're almost there. Get that outside function. Aurelie, good job for number 1. Brian V has a question mark drawn, but that looks beautiful, Brian. I think that's good for all 3 of them, actually. For all 3 of them. Brian N, good job for number 1. Number 2 has question marks, but that's not wrong, Brian N. That's not wrong. It's just not going to help us, but that is not wrong, right? But f of x equaling x, we call that the identity function, which means that it's just equal to itself. It doesn't, nothing gets modified, and that's not wrong. Calvin, good job on number 1. Frankie, good job on number 1 as well. And there's 10 of you guys who didn't respond. What happened here? There's 10 of you guys who did not respond. Are you just waiting? Works a little bit more if you try it, right? It helps a little bit more if you try it out. Okay? It helps a little bit more if you try it out. So one of the tips I like to do when I start dealing with composite functions is if it doesn't have parentheses, put parentheses on them. And it helps you to see what or where the inside function is, and hopefully that will help you see what the outside function is. Number 1's already written out like that for us. Okay, number 1's already written out like that for us. So I'm going to go ahead and move this down a little bit so I have a little bit more space. So I'm telling you right now that I can see that the inside function is this guy right here, right? And then the outside function is this stuff being raised to the 4th power. So when I asked what's the inside function, I'd say g of x in this case is equal to 3x plus 5. That's literally on the inside of, well, what's the outside function? My outside function is some stuff to the 4th power. Traditionally, though, we write this as x to the 4th, right? But I've gotten, yeah, so that's the idea. The outside function is some stuff to the 4th power. But for our sake, right, for our sake, I'm going to start writing functions like this where they have the outside function. I'm going to start writing it using parentheses instead. Now, this is not the right way to break down a function. This is the right way to break down these functions. But I'm breaking it down like this incorrect way because it's actually going to be a nice shortcut for us for when we use the chain rule. And you'll see it in a second. So let's go back over here now. So let's take a look here. I'm saying I should rewrite this using parentheses. And this right here, this function would actually look something like this. You see that? Sine of 2x is sine of 2x, right? And that tells me then, what's the inside function? The inside function is this guy right here. What's the outside function? This guy right here. That is the outside function, right? So if I was breaking this down, my inside function here, g of x, is going to equal to 2x. See that? The outside function then would be f of x is equal to sine of x. But again, I'm going to write it the incorrect way, right, to help us today with our notes. It's going to be sine of some stuff, right? What's that stuff? Oh, that stuff is just whatever I have here that's going to get plugged into here, right? And the last one right here, tangent of x, is, again, rewrite this using parentheses to make your life a little bit easier, right? This would be sine, I'm sorry, I looked at the wrong problem. Tangent, right? Now here's the tricky part. Where's that squared go? When it's on the trig function like that, it's not x squared, right? It's not x squared. It's actually everything here. Actually, not everything, just the trig function squared. So it's tangent of x squared, right? That's the notation, by the way, for tan squared x is sine squared x, cosine squared x. That's the notation we use to tell you that you're squaring this trig function and the stuff that's inside it, right? Well, not the stuff that's inside it. You're going to do the trig function of that stuff that's inside it and then square the whole thing. Okay? So what does that mean for our answer here? Well, our inside this time is tangent of x. The outside is some stuff squared, right? So I have here g of x is equal to tangent of x. And then I have here f of x is equal to x squared. But again, I'm going to write it like this, which is some stuff squared, which actually makes it a little bit easier to see your outside function. Do you guys see that? Hopefully you do. And again, if you're struggling with this because you don't remember learning composite functions, you got to stop by during my office hours. And it is something that you need to nip in the bud. Nip in the butt? Something you have to take care of early on. It's a problem. If you don't see it now and you don't do something about it to learn about these composite functions, I've seen it before. It wasn't many students, but those students who did struggle with this, it carried on to other chapters, and we need to like stop it here. All right, so let me know if you don't get it. We can work on composite functions and identifying these inside and outside functions, okay? And why do we need to define these inside and outside functions? Well, it basically comes down to this, and here it is. Once you find those things, to take the derivative of them, it's actually fairly easy. And we use this thing called the chain rule. I know earlier I was like, well, where do we use the chain rule? But I didn't actually tell you what it was. Right? The chain rule is this. If I have a function, right? If I have a function, y is equal to f of u, again, don't giggle, is a differentiable function. Right, is a differentiable function of u, and u is equal to g of x, right? Is a differentiable function as well. This is the key thing. Both the inside function and the outside function need to be differentiable, right? The differentiable function of x, right? Then y is equal to f of g of x is a differentiable function as well. Right? Of x, and this is the part that's a little weird. This is how they define it in books, and if you ever Google chain rule, this will probably come up for you if you're looking for dy dx. This is going to equal to dy du times du dx. And you go, what the heck? And that's not the one that we like. I mean, that's the main definition of it, but the one we traditionally use is this one right here. If I take the derivative, right, of a composite function, f of g of x, right? This is going to equal to f prime of g of x times g prime of x. And what this is essentially saying is you're going to end up with the derivative of the outside function evaluated with the inside function times the derivative of the inside function. Right? That's the main thing, is you have to understand when you take this derivative, you're just multiplying the derivative of the outside function times the derivative of the inside function. You're like, what? At least if you're like me, that's how I was when I saw this. It's like, what? Right? So, I never finished this problem for number 2. But let's go ahead and do that real quick. It was 2x plus 3 to the third power. You ready for this? Let's break this one down. All right, let's do an example of this chain rule. Were you guys able to copy down that chain rule? I'll put it right there just in case you weren't, and I'll put down the example for those of you who already have it copied down. Let's say I was asked here to find, right, dy dx equaling to 2x plus 3 to the third. That's a 2, Knock Me. You said third. Yeah, right. Thank you, Knock Me. All right, so that is the question that we're going to be looking at. That's the example that we're going to be looking at. Hopefully you guys are okay. Were you guys able to copy down the chain rule? I'm going to go ahead and slide this down in a second here. But if not, I want to give you a second to write this down. If you're looking to just take efficient rules, let's get this part. This is the main one that we're going to be using, right? The idea is if you're taking the derivative of a composite function, first thing you got to be able to identify that it's a composite function. Identify what's inside, what's outside. And then all you're going to do is take the derivative of the inside and multiply it with the derivative of the outside. You ready? Here we go. Just in case you need it still. So I like to go in there and identify what is the inner function, right? What's the inner? And in this case, the inner is equal to 2x plus 3. And then I do the same thing and I go out there and I list out what's the outer. What's the outer function? And the outer function here is supposed to be x cubed, but I'm going to write it like this just for you to see it. It's easier to deal with this way. Okay? I'm going to write it like so. Now, what's the derivative going to be equal to? Whoops, that's horribly written. Knock Me, what the heck? That's saying the derivative is equal to that. I'm just looking to find the derivative, right, for y equals to that. My goodness, Knock Me. Get it together. All right, so to get the derivative of this, right, dy dx is simply going to equal to the derivative of the inside function. What's the derivative of the inside function? The derivative of the inside function, let's do that real quick. If I take the derivative of this, right, if I take the derivative of this, that's just going to equal to 2. And if I take the derivative, and that's just going to equal to 2. I'm going to write that down. Derivative of the inside function is 2. And then that's going to multiply. Oh, thank you, Monica. I just saw that right now. Yeah, the derivative of the inside function is 2. And then I'm going to multiply that with the derivative of the outside function. Dx of the outside function is going to be 3 times some stuff squared. Now, traditionally, right, if I had written as x cubed, the derivative of that would be 3x squared. You see that? Using the power rule, right? But what I can say is this, that x could be literally just written as some stuff. That's all I'm saying. And what that stuff is what was plugged inside earlier, right? Because that's what this composite function is built of. It's built of that stuff that's in here with a candy shell on the outside. Now, when I take the derivative of the outside, I end up with this, which is going to be 3 times some stuff squared. Well, what's that stuff, though, Knock Me? What was the inside function, Knock Me? That inside function was 2x plus 3, and I simply just write that down. And that's my derivative, guys. That's my derivative. I can clean this up if I want to. I could simplify this out. dy dx is equal to 6x times 2x plus 3 squared. You could FOIL it out if you want to, but most of the times, like I said before, you don't need to, right? You don't need to simplify unless there's more problems that you're going to need to take the derivative again, and I don't want to use the product rule, or it's a multiple choice problem and you need to select the correct one. Okay, but in this particular case, you're good. You're good there, right? You don't need to do any more. But again, the idea is this. When you're taking the derivative of a composite function, you identify what is the inner function and what is the outer function. And then the answer, the derivative for that composite function is just the derivative of the inside, derivative of the inner function, and you multiply that with the derivative of the outer function. So you got an inner function and you got the outer function, and you just take the derivative of those guys. right there. You guys okay, or is it like, what the heck? Let's do another one. Why is it 6x, not 6? You're right. Why'd I put an x there? That never happened, Brian. Or that never happened, Oscar. Wow, I made 2 mistakes in a row. Not only did I write that wrong, I also got your name wrong, Oscar. But yeah, you're right. Good catch. Good catch, Oscar. You are right. It is supposed to be 6, not 6x. Why did I write an x there? We'll never know. All right. Good job, Oscar. That shows me that you're paying attention. I like it. I like it. All right. Let's see here. I got a couple examples here. Let's have you guys try a couple of them, okay? So let's go ahead with a new page and have you guys try these next ones up. Let's go. Here, you try. Number 1. Okay, let's go with find dy dx, and we're going to go with y is equal to 3x minus 2x squared to the third. Try that one out, and if that one is too easy, try this one. Number 2. Let's go with find. Let's write it using another notation instead of dy dx. Let's write it using y prime, given y is equal to the cube root of x squared minus 1. Try that one. See if you can get that one. If you get the first one too easily, see if you can get the second one. Let's go ahead and set a 5-minute timer for this. All right, try this out. Try the first one out, see what you get. Write down the answer into the Pear Deck for me, and try the second one. The second one's a fun one for some people. I need to find out how to give you guys cardinal cash, because when you catch mistakes like that, that is definitely worthy of cardinal points. Let me figure that out right now, actually. PBIS rewards. Is that what I need to click on? Remind me later. Okay, let's see here. Search up student. Oscar Vasquez. Let's go with ownership. How much can I give you? Corrected teacher mistake in class. By the way, are any of your teachers giving out cardinal points? You guys know? I know none of the other math teachers have been doing it. I wanted to start because they actually told us that you guys can redeem them for stuff. No, it's useless currency in my eyes. David saying yeah, Emily saying yeah, Jackie saying yeah, Sam no, Julia no. Okay, so it's like a pretty split. I haven't gotten some since 9th grade. Oh, geez, Brian. Joe saying no. Yeah, I'm not gonna lie. I'll admit it. I was one of the bad teachers at it. They are unwanted. I don't ever use them though. Yeah. So they're making it a little bit easier now, so to redeem because of the whole COVID thing. I didn't get any at all 10th grade. Yeah, they used to have good stuff though. I remember maybe your 10th grade year, they had like movie tickets all the time that you could buy with them, right? You can get like movie tickets. You can get Starbucks gift card. What else do they have? I think they had In-N-Out gift cards too. And then they also had like little battery packs if you guys needed a USB battery pack to recharge your stuff. They had all that. Yeah, they had all that stuff. I remember looking at it. They had like a poster and a flyer. But the problem was, Eric, you'd have to go on like the second Tuesday of the month or something like that. It was very specific days, and it was either during nutrition or lunch. You couldn't even go after school. You had to go during your lunchtime, and if they had a line there, you had to wait in line to get it. So I know a lot of students didn't care for it because it was just too much of a hassle to get your stuff. But I know now you can fill out some forms, I believe. I'll look it up. I think you guys should start looking up, and I should start handing out more points, especially for those of you who are doing this on the Pear Deck. I appreciate. Like I said, I always appreciate you guys writing on there. Even if you don't know what you're writing and you write it wrong, I appreciate that you're on the Pear Deck writing, because it makes me feel like I'm not talking to a screen. Well, I mean, I'm talking to a screen, but I'm also, have someone to interact with. That's our way. Even though, sometimes your drawings are not supposed to be drawn on there, I still appreciate it. Yeah, I still do. All right. Anyways, that's me rambling, talking about nonsense. I do, David. I do appreciate your drawings. Looking good, Calvin. That work for the inner and the outer is good. Now get the final answer. What do you do to get that final answer with that stuff there? Kimberly. Yeah. Oh, yeah. Keep going. You're almost there. I'm stopping you. You're doing good. Max, looking good. Looking good. See if you can get that second one. You got the inner for that second one. What's the outer for that second one? That's going to be a fun one. I'm telling you. Stop saying it's fun. No, I'm telling you, it's fun, guys. It's fun. You don't believe me, but it's fun. You might not believe me, but it is fun. All right. It's been about 5 minutes. I like the answers written here. Let's take a look here. Let's see if I can show off some of these for the answers you guys got for number one. So I'm going to go ahead and star some of these. Let's share them on screen with everybody. Yeah. So let's go ahead and share these out. So let's go with that one, that one. How many more? Pick one at random. I mean, that's an interesting one, David. All right. So let's go with that one, and let's go ahead and share these results. Let's take a look here. How did you guys do as a whole? Oh my God, my computer is lagging hard. Let's close some of these things because having many tabs open is not good for my computer. Let's go ahead and show these responses that we have here. First one up for number one, beautifully done, right? If you look back here, the inside function is 3x minus 2x squared, and the outside function is stuff to the third, right? So when we go back over here, the inside function derivative is going to be this one right here, I believe, is the 3 minus 4x, because the derivative of 3x is 3. Derivative of 2x squared is 4x. That's beautiful. Multiply with the derivative of the outside is some stuff being cubed. So you bring down the power, and it's some stuff now being squared instead. And that's it. That's your answer. You're done, right? Number two, good job. The inside function is ax squared, so the derivative of x squared is 2x. Beautiful. We just need the derivative of the outside function, right? This next student, same answer for number one. Beautiful work. And same thing over here. Beautiful work for number one. I like your choice of your color, right? Good job, guys. Awesome work there. So that was number one. You guys had really no issues on this one, right? If you guys did, you guys got to let me know if you are struggling with this, right? Because based on what I'm seeing, it looks good. Get out of here. It's going to be 3 minus 4x, right? That's the derivative of the inside multiplied with the derivative of the outside, which is 3 times 3x minus 2x squared. Bam. Right? You could do it like that, or you could do it like how everyone else did it, which was like that. That works as well. Okay? That works as well. Again, what helps, I'm telling you, is list the inner, right? And the inner function in this case was 3x minus 2x squared, and then list the outer. And the outer function is some stuff cubed. Once you see it this way, you can actually kind of identify, well, the derivative of this is that, and the derivative of this is that, right? But the only thing is what goes on the inside. What goes on the inside is what we had as defined as our inner, and that's it. And that's it. Number 2. Now remember what I tell you. You can probably see the inner function and the outer function, right? But some of you guys might not know what the derivative of this cube root is. And that's why I'm telling you, one thing that helps is to rewrite it using parentheses instead of the symbols that are there. You can rewrite this. You guys know that, right? This is going to be x squared minus 1 to the 1/3 power, right? To the 1/3 power. That way you can see it a little bit easier that the inside function, which is, by the way, still x squared minus 1, right? But now the outer function will be a little bit easier to deal with because now it's just some stuff to the 1/3 power. And that's, I swear I'm doing that a lot today. And that's just pretty much the same thing as something to the 3rd power when you're applying the power rule. I'm not saying the functions are the same. I'm saying when you apply the power rule, the power rule applies the same way to this outer function. You ready? So let's say here, I was taking the derivative of this guy. The inner function, derivative of the inside function, is going to be 2x, right, times the derivative of the outside function. Well, the power is 1/3. I just bring that power down. 1/3 times some stuff to the 1/3 minus 1. And 1/3 minus 1 is negative 2/3. What's on the inside? Some stuff. The same stuff I had earlier as my inner stuff. That's all it is. My inner stuff, it was what goes inside there. See that? And that's it, guys. That's your answer for number 2. You could simplify it, right? If you needed to, just do a little bit of algebra, but the calculus part of it is done. Calculus part of it is easy, guys, right? How do you feel about that? What do you guys think? Inner, outer, do you feel okay? Do you not feel okay? Is it weird? Is it not weird? Let me give you a chance to answer here. All right, David. That's a pretty good banana pencil. Not gonna lie. Distracted me, of course. Here's what I need from you guys. Can you guys tell me how you feel about this? Just thumbs up, thumbs down, or somewhere in between. Move the dot to where you feel, and let's see how you guys feel as a class. I'm so fidgety right now. Go ahead and let me see here. It looks like majority of you guys are feeling pretty good. That's good. That's good. All right. That's good. Let's go and let's keep going. Let's keep going. So the next part I wanted to show you is applying the chain rule to trig functions, right? Because you guys saw earlier, right? If I asked you to take the derivative of sine x, right? If I asked you to take the derivative of sine x, right? You wouldn't sine x. If I asked you to take the derivative of sine x, you guys would be able to tell me that's just equal to cosine x, right? But what happens when you have sine of 6x then, right? What happens with the derivative there? And it's the same concept. It's the same concept, right? The inside function is 6x, the outside function is sine, and you just multiply them together. So the derivative of the inside is 6, right? Derivative of the outside is cosine of some stuff. It's not cosine of x. It's cosine of 6x because that was the inner function that we deal with there, right? So you got to keep that in mind, right? So whatever is inside the trig function, when you take derivative of sine, you get cosine, but the stuff that's inside stays the same when you take the derivative, right? And then don't forget to multiply by the outside. And I'm going to give you guys these rules right now. Give me 1 second here. I'm feeling lazy. There we go. My computer is lagging today. What is happening? Why are you lagging today? I think you need to restart after this class. But here we go. That noise was supposed to play a long time ago when I made that copy, but you know, it is what it is. So this is the chain rule version of the derivatives of the 6 trig functions that we've learned before. And it's nothing new, right? If you had sine of u, the derivative of sine would be cosine. But if you have an inside function, then you multiply by the derivative of that said inside function, right? That's all I'm trying to show you guys. Have you memorized your derivatives of your 6 trig functions yet? If not, you should get on that, right? You need to know sine, you need to know cosine, that's for sure. But you should know derivative of sine is cosine, derivative of cosine is negative sine. If you haven't learned that yet, you're going to have a rough time. Okay, so make sure you get that down. The next one up that you need to learn for sure is tangent, right? Tangent, derivative of tangent is secant squared. And then after that, once you go to cotangent, secant, and cosecant, you don't really need to memorize them, but it makes your life a lot easier if you do. It makes your life a lot easier if you do. Okay, so try to get those down. Make flashcards, do something. You will have to know them forwards and backwards, right? So get them down, get them memorized, and you'll be a lot happier in the future. So let's do an example real quick, and then we can hopefully move on to a little bit more complicated problem here. So I'll leave that right there so you can write that down. But let's do an example real quick. I just wanted to show you guys real quick, right? So I showed you one earlier with sine, right? So I've had y was equal to sine of 6x, right? The inner, right, showing the work here would be 6x. The outer, you already have this written down, so you don't need to write it again, but it helps. The outer is this one of sine of some stuff. What's that stuff? Why that stuff is just the 6x. So y prime is equal to derivative of the inside, which is 6, multiplied with the derivative of the outside, which is cosine of some stuff. But what again, what's that stuff? 6x. Like so. Okay. Let's do another one. Let's take a look here. Let's say I have y is equal to cosine of 3x minus 1. Same thing, right? What's my inner function? Inner is 3x minus 1. What's my outer function? Cosine of some stuff. Which tells me then y prime is equal to the derivative of the inside, which is 3, multiplied by the derivative of the outside, which is negative sine of some stuff. But knock me. Pertot, what's that stuff? It's just the 3x minus 1. That's your answer. Right? So, chain rule applies to these tangent functions, applies to other functions as well. Your job is to identify what's your inner function, what's your outer function, what's the gum center and what's the candy shell, right? What's the gum center and what's the candy shell on the outside? Once you identify that, the derivative of the chain rule is just, well, that. Okay? All right. Let's talk about this real quick here. What happens if you have more than 2 functions building your composite function? Right? What happens if you have more than 2 functions building your composite function? So for example, what if I had this instead? What if I had this instead? Let's say earlier I told you guys y was equal to the cube root of x squared plus 1, right? The cube root of x squared plus 1. But what if instead I wanted to make it a little bit more complicated, a little bit more challenging? Let's say it was the cube root of x squared. Wait, was it plus 1 or minus 1? Minus 1. X squared minus 1, right, squared. Here's the thing, right? Your inner function, which before, my inner function, right, was x squared minus 1. And then my outer function was the cube root. Okay? That was my inner function. That was my outer function. There's another function in there. Do you guys see it? Do you guys see that other function? How would you denote that using parentheses, by the way? What's that other function? Any ideas? You probably already spot it, but I just want to give you guys a chance if you haven't seen it yet. What is that other function that's being involved that I haven't written down yet? I hope you guys see it. It's this function right here. The stuff inside being squared. Do you see it? If I rewrite this function, this is x squared minus 1 squared, and then being raised to a 1/3 power. I have here an inner function, a middle function, and I have an outer function. This composite function is built on multiple functions put together, not just 2, but 3 of them placed together. I have this little piece of gum that's inside this candy wrapper, that's inside a plastic wrapper. So there's 3 levels there. Yes, you could do that. You want to do it that way instead, Eva? I'm sorry. Wow. Ava? I should know that. But yeah, you could do that, Ava. If you want to rewrite it like that, that's perfect. That's beautiful. And then you don't have to worry about that. And that's a good workaround. So you can write it as, let's do that. I don't know if you guys saw that, but you can do that. You can rewrite this as x squared minus 1 to the 2/3 and just apply the inner and the outer. And you don't need the middle ground anymore, do you? And you're done there. That's awesome. Now, can you do that all the time? Will that always work? And of course it's not, right? And why else would I bring this up? What happens when you can't rewrite it into something where you just have an inner and an outer? Then we got to deal with this guy with the middle. Okay, so let's do one where we can't rewrite it. Let's do one where we can't rewrite it. You ready? Y is equal to sine to the 4th power of 3x. Sine to the 4th power of 3x. So let's look at this problem real quick. Okay, let's take a look at this problem real quick. So let's say here, I have here sine to the 4th power of 3x. This is the part that I need you to see, right? Rewrite this using parentheses so it's a little bit easier to deal with. So I have here y is equal to sine of 3x all to the 4th. And I hope you guys can break this down. Let's go piece by piece. The innermost function is 3x. The outermost function is some stuff being raised to the 4th power. Well, what about the part that's in the middle? That's this guy right here. I'd say we call that just the middle function. And the middle function in this case is sine of some stuff. And how does this work? The 3x goes into here, and then the sine of the 3x goes into there. The chain rule works for composite functions of composite functions as well. If you have a repeated composite function, you have a center that's inside a gum center that's inside a candy shell that's inside a plastic wrapper, the chain rule works here as well. We take the chain rule, and to take the chain rule for this one, the derivative of this, right, is going to be equal to the derivative of the inner function, right? Derivative of the inner function, right? Derivative of the inner function in this case is 3. Multiply that with the derivative of the middle function. Derivative of the middle function is cosine of some stuff. But what's the stuff that's in there? It's the 3x from earlier. You're almost done. Now you take that and you multiply that with the derivative of the outer function. And the outer function is 4 times some stuff to the 3rd power. Well, knock me. What the heck is the stuff that goes inside there? It's going to be sine of 3x. And that's your derivative using the chain rule on something that is built up of multiple functions, right? Something that's built on multiple functions. Your inner function, your middle function, your outer function. Okay? And honestly, the chain rule is actually one of the more fun rules, I'd say, to apply to functions, right? You just have to identify them. And I guarantee you, that's the main mistake that students make, is identifying what's the inner function, what's the outer function, and how to apply these derivatives to them. Okay? Yeah, let's try one. Let's try one. Here, take a look. Let's see if you can try this one. Okay, I'll leave this example up here. You try. Okay? I'm gonna give you a blank one right here, and I want you guys to try it. So give me 1 second here. Get you a blank screen. We'll go over to here, and let's go with this blank screen right here. And I want you guys to try this one problem, right? Once you do multiple chain rules, it just gets really messy. So we're just gonna do this one problem. See if you can figure this one out. Okay? Y is equal to the square root of secant x over 2. Try that one. Try that one. This one's a little bit more difficult, so I'm going to give you guys about 4 minutes on 3.5 minutes on this one. I think you guys are doing 3.5 minutes. So go ahead and try that, see what you get. And if you don't know how to start and you don't think you can get the answer, just list on the pair deck for me what's the innermost function you see there, what's the middle function you see, and what's the outermost function you see there. At least start off with that and just list out those things. And don't worry about being wrong, right? This is the time you want to try, and if you get it wrong, don't worry about it. Let's just see what you get. Let's just see what you get. I'm gonna snack on some stuff while you guys are doing that. Have you guys had these chili mangoes? Pretty good. Pretty good. Is there a small piece? I don't want a big piece. Oh, that's pretty big. Oh. There's so much sugar on them, but I think that's what makes it delicious.
According to Merriam-Webster, 1. Affording great.
All right, Google, stop. Knock it off. I did not say your name at all. All right. Ooh, Jocelyn, I like your choice of colors. Good job, good job. Max, that is beautiful. You have it inner, middle, and outer listed perfectly. You want to go ahead and finish that off and tell me what the derivative of each of those ones are, and then multiply them out, because that's pretty much it. You've done the hardest part. Get the final step. Julia, same to you. Beautifully written, right? Beautifully written. Get the derivatives and multiply them out, and you're pretty much done. Kimberly, I like yours. You got your inner written. I'm assuming that's going to be your middle. And you keep going. Good, good, good. Leslie, beautiful. You guys have it. Wow, this is beautiful. Good job. You have them listed beautifully done. Go ahead now and start doing the derivative of each one. You guys got it. You guys got it. Oscar, awesome job. Monica, awesome. Leslie, I think I already said it, but Leslie, awesome job again if I didn't say it earlier. Or if I did. Kaylee's going with the answer. Kaylee's going with the answer. And Kaylee, you're close. Kaylee, oh, you're so close. That is, or am I blind? I think you're like pretty much there. I think you're just missing one thing somewhere on the middle derivative. But other than that, I think that looks really good. You're just missing one little thing. Emily, awesome job listing it out. Good, good. Okay, stop being so angry at me. There we go. All right. Just to finish off the people who are working on it. Gracie, beautiful. Brian, you're almost there. You're almost there. Your inner and your middle derivatives are beautiful. Just got to work on that last one, on the outer one. Brian B. Brian N, good job listing all the functions. Go ahead and try to take the derivative of each one and let's see what you get. Angela, awesome. Don't forget about the outer, or actually, I think you're thinking about the outer. David, you're so close. That last one, I think you're a little overzealous on that last one. You were so close on that one. Orange, you're glad you didn't draw a banana? Let's see here. Yes, that's going to sound like nonsense, by the way, in the recording, but that's because David drew a banana earlier, and now he drew an orange. Ava, good job on the derivative on that first one. That's beautiful. Areli. Oh, you're going for it. You're just straight up going for it. Okay, that's good. I don't know what's right, but thank you for that. I appreciate the attempt. All right, let's go ahead and go over this before the end of class here. And let's go ahead and take a look here. All right, again, what helps me sometimes is to rewrite these using parentheses, honestly. Right? X over 2, and this whole thing is being raised to the 1/2 power. That's usually what helps me. And it doesn't help everybody, but it helps me. And I think it would help most people, but some people don't like doing it. And I leave that choice up to you, right? I leave that choice up to you. And I like to write these out, right? What's the innermost function I see here? The innermost function I see is x over 2. The middle function I see here, let me keep the same colors. I did my middle functions in green. Let's go with the middle function, right? Being secant of x over 2. And the outermost function, right? The outermost function I see here is some stuff to the 1/2. And that stuff is the secant of x over 2. So when I'm taking the derivative of this guy, I literally just need the derivative of each level, okay? I need the derivative of each level. So, you know, what might help is if you make like a table and write out the derivatives next to it. That was a terrible table. So let's go ahead and write this over here. And the derivative, right, if I take the derivative of these guys, the derivative of x over 2 is just 1/2, by the way. It's like 1/2 x, so I take the coefficient of it. So that's the derivative of the inner function, by the way. All right, x over 2 is the same thing as 1/2 x, and the derivative of 1/2 x is just 1/2. Okay? All right, the derivative of secant, right? The derivative of secant is secant x tangent x. Secant x tangent x, right? But in this case, I'm not going to write it as secant x tangent x. I'm going to write it as secant stuff tangent stuff. Knock me, what's the stuff? What's the stuff? Knock me, what's the stuff? It's the x over 2. That's all it is. It's x over 2. That's the derivative of the middle function. Last but not least is the derivative of the outer function, which is going to be 1/2 of some stuff. Knock me, what's the stuff to the 1/2? Negative 1/2. Knock me, what's the stuff? What's the stuff? Stuff that's in there is going to be secant of x over 2. And again, why do I like the chain rule so much, guys? I just take all the stuff I just found there, I just multiply them all together. So my chain rule tells me that the derivative of this is going to be equal to 1/2 times secant of x over 2 times tangent of x over 2. Okay? Times 1/2 of secant of x over 2 to the negative 1/2. And that's my answer. I guarantee you, you plug this into Desmos, you are going to get something that's overly simplified. And I don't want that. I don't want that. I want this. Okay? I don't want you to simplify. And I promise you, if I do give you a problem like this, I'm not going to ask you for something that will go a little bit crazier than that. I might ask you for the second derivative. That seems like a fun problem to do. But yeah, nothing too crazy. Okay? All right. Give me a second here. Let's wrap it up for today. I want to do one final check-in with you guys. How do you feel with these chain rules? Okay? How do you feel with these chain rules? I'm going to post up the homework later today. You guys can start doing these practice problems just to see how you feel. Okay? Just to see how you feel. I'm going to move it back onto the screen. Move that thing where it would need to go. Wouldn't the exponent be negative 3 over 2? I don't think so. Is this right? This is a 1/2, right? Monica, that's a 1/2 because the square root is just 1/2. It's not a negative 1/2. So when I do 1/2 minus 1, right, that's the same thing as 1/2 minus 2 over 2. I think it's negative 1/2. I think it's negative 1/2. I think that's right. Or are you seeing somewhere else? Because the power rule just subtracts that from 1. Yeah. But thank you, though. I appreciate that you're checking. You're double checking my work. And then you're not just taking my word for it. I know that sounds weird coming from a teacher, but I've heard in the past that other students say they're afraid to correct their teachers because their teachers would get angry if they correct them. I don't understand that. I'd rather you correct me because I don't want to be teaching you the wrong math stuff, right? Anyways, looks like none of you guys are changing your temperature check anymore, or your dots. So looks like you guys are doing all right. And yeah, that seems like a good place to stop there, guys. So I'm gonna have your homework posted later today, and you can do some more practice problems, and then we're almost done with this thing right here. We just need to talk about using it for like a table and calculating like specific derivatives like log and natural log, and we need to look at those guys later. All right, guys. So anyways, that's it for today, guys. Have a good rest of your day. I'll see you guys on Thursday, okay? Yeah, and that's it for me, right? Have a good rest of your day, and have a good Wednesday tomorrow, since I won't see you.